this one y boundary, here 0 and here this is the velocity profile or velocity distribution. This one is velocity profile for fluid, profile or distribution for fluid. And suppose this is the V, this is the velocity, and there is two layer. One is consider A lever, this is B layer. Already I said when what is viscosity? Viscosity means it is the property of fluid which offer resistance to movement of one layer. This is one layer, this is another layer. Offer resistance to the movement of one layer over another adjacent layer. This is suppose adjacent layer. Adjacent layer of fluids. Actually this, suppose layer 1, layer A, this is layer A. Now this one is I draw in the a big plane. Suppose this is the layer A, this is the layer B, this is Y, and this is U. At layer there is a velocity is U, distance Y, and velocity is U. After this, at here the perpendicular distance is y into dy, and the velocity is u plus du. Means at layer A lower velocity, but at layer B the velocity is higher. So you can say at layer A and layer B moves, and layer A and layer B moving different velocity, and there is a so there is a relative motion between them. There is relative motion between them, and the layer A moving lower velocity, but lower B moving higher velocity, and they offer resistance each others, and layer B in its motion feel a resistance, a resistance and layer A also a resistance. This is called viscosity. This is the viscosity. For solid body, this is suppose solid body. When the feel a resistance, there will occur a shear force, and due to shear force there will be a shear stress. When shear force always acts parallel to the surface, and this is suppose dF for solid, A B C D is A dash B dash, and this is the shear angle. This also the shear angle. At this condition, strain is constant. Deformation does not change with respect to time. But in case of fluid, continuous deformation with respect to time. This is fluid. A continuous deformation with time, or shear strain is not constant. Shear strain is not constant for fluid. Understand? Now, Newton's law of viscosity. Suppose this is the solid boundary, and here a particular layer. This is suppose a layer. This is A point, this is B points. Here is a du, the velocity is du, and this distance is dy. After d time, then occupy new position at C. The new position. This distance always velocity into time, and this is the shear angle. So tan phi equal to du into dt by dy. Phi is so small, so tan phi equivalent phi. Suppose this is the d theta, phi not, this is suppose d theta, the shear angle is d theta. So this is the d theta. D theta is so small, so tan d theta equivalent d theta. So d theta equal to du into dt by dy. So d theta by dt into dy by dy by dy. You can say this is the rate of shear strain, rate of shear strain this is the velocity gradient with perpendicular direction of in perpendicular direction of gradient in perpendicular direction of flow. And from the Newton's law of viscosity, shear stress directly proportional to the rate of shear strain. So shear stress is directly proportional d theta by dt, and from this equation velocity gradient du by dy, and we draw this proportional limit, get a constant du by dy. This is the equation of Newton's law of viscosity. This mu is dynamic viscosity or absolute viscosity. Understand? Unit of mu from the Newton's law of viscosity, du by dy. So mu equal to dy into du. The stress unit is Newton per meter square, and this is the length meter. Du means meter per second, so meter cancel out. The unit of this one Newton second meter square. This is the SI unit, and centimeter second, dyne second per centimeter square, or OS. This is one is the CGS unit. This one is CGS unit, and the relation between CGS 1 OS equal to 0.1. This one is also Newton Pascal per seconds. You can say Pascal per second. This is the relation between CGS unit of viscosity and the understand. Next is kinematic viscosity. Is denoted by mu. Huh. It is the ability of fluid ability of fluid. This is the ability of fluid to diffuse or diffuse a disturbance in molecular momentum in molecular momentum molecular momentum, and the kinematic viscosity nu equal to dynamic viscosity divided by density. The unit of kinematic viscosity, SI unit is meter square per seconds, as CGS unit is centimeters square per second, or Stoke. So one Stoke equal to 10 to the power minus 4 meter square per second. This is the units. Now, effect of temperature on dynamic viscosity. For liquid for liquid the viscosity equal to viscosity naught 1 plus alpha t plus beta t square. When temperature is rise, molecules kinematic energy of molecules of liquids also increase, and they try to far away from each other also increase. So attractive force between them is also so cohesive force decrease, and the resistance against in motion or in in motion is also decrease, so viscosity also decrease in liquid. I already said for liquid, cause of viscosity, reason of viscosity is mainly cohesive force. In liquid, cohesive force is decreased, so viscosity also decrease. Here mu naught equal to viscosity of liquid at 0 degree centigrade, and alpha and beta are constant and alpha greater than beta. For gas, viscosity equal to mu naught plus alpha t minus beta t square. Understand? When temperature is increased, momentum of molecules increases, and collision between them also increases, and more frictional force exerted, and resistance against inflow is also increases, so viscosity is also increases. I already said for gas, the intermolecular momentum transfer for reason of viscosity.